Thanks a lot for the reminder. Thank you. And okay, let's continue. So for the Poisson regression, we will assume that the response follows a Poisson distribution with random with this Poisson parameter equal to lambda I. And we do have this Poisson assumption because our response values are all non-negative integers. So this will be a good fit for the read count in the D analysis. And the regression structure will be that the log of lambda I is a linear combination of the predictors. So if we have p minus 1 predictors, this will be the formula, the sum of beta k times xik, where k from 0 to p minus 1. So here we need this log transformation on the Poisson parameter because the right-hand side will take values from negative infinity to positive infinity. And however, this lambda are only values which are non-negative. So we need to take the run log transformation to make sure that the left part and the right part have the same range. And this is the structure. And let's go to the example that we stopped yesterday. So yesterday we were looking at the simulcount Poisson dataset, which is a simulated dataset which was generated by myself. In this dataset, each row is a biological sample and each column is a gene. And the entries are read counts. So let's look at the dataset again to see what the data look like. So if we go to the dataset and use this function read.table to read this dataset, we can have a look at what the dataset look like. So if we have a look at this dataset, we will see that it has 10 rows and 200 columns, and each row is a biological replicate and each column is a gene. From the name of the biological samples, you can see that the first 5 samples are from a treatment condition and the last 5 samples are from the control condition. So that we want to compare these 2 conditions for each of the genes to see whether each of the genes have different read counts between the 2 conditions. And if we use the regression model, we will make the condition as a predictor and the read counts as a response. So this focused on the first gene first, so which means that we only want to do one linear regression for this gene and use the condition label as the predictor and the gene counts, read counts as the response. So we will first get the count vector of that gene, and we can name it as count. So here we just extract the first column of this dataset and name it as count. And then we can generate our predictors. So here we need to generate our predictors ourselves because we don't have that information from the data itself. We interpret the condition from the data because we know we can, from the names of the samples, we know that the first 5 are from the treat condition and the last 5 are from the control condition. So we can generate our predictors ourselves. So we can use this command to generate such a vector. So the rep treat5, this command will give us a vector with 5 treats, and this will give us a vector of 5 controls. And then we can use C to combine these 2 things together so that we will get a vector of 10 strings. The first 5 are treat and the last 5 are control. And this will be the conditions of our samples, and we can use it as the predictors for this D analysis. And then we can combine these two things together so that the dataset will be in the format which is similar to our previous regression models, so that we use this data.frame function to combine these two columns, these two vectors together, and make each of these two vectors as a column of the data frame. And then we look at the output of this, we can see that in the de.data, this data frame has two columns. The first column is count, the second column is condition, and it is described, and these two columns describe the predictors and the responses for our first gene. And then we can use a regression model to see whether this gene is a D gene or not. Here we will use the GLM function to do the regression. We will use LM to do linear model, and we use GLM to do generalized linear model. And the first part is the formula of the regression. We want to predict count using condition. So this is the format. And then we also have a data argument, which is the name of the data set we are using. And the final argument, input argument, is the type of regression we are using. Here we are doing Poisson regression. So we make family equals to Poisson. And within the Poisson, we will have a input argument, which is link function. This link function means the relationship between the response and predictors. And we go back to the formula of the Poisson regression. We can see that the log of the parameter will be the linear combination of the x. So the log here, log is the link between lambda and this linear combination. So it is why we say Poisson link equals to log. And this will be the formula for this generalized linear model. And if you still remember, for logistic regression, we will change the family equal to binomial. And that was for the family for logistic regression. Here we are using Poisson regression. So we make family equals to Poisson. And we all have an extra part, which is the name of link function. And now we can run this command. And then we get the output of the generalized linear model, and we name it as model 1, and we can run summary model 1 to see the results. So we can see from the results, we can see that we have the estimated coefficients for this condition treat, which means that if the treatment condition from 0 to 1, we will have a positive coefficient, which means that we will have an increase in the gene expression levels. And we can, if we look at the p-values, we can see that the p-value is very small, which means that this is the relationship between condition and count is very significant. Okay. And yeah, that's the output of the generalized linear model. And if you have not finished it, you can also try these commands on the dataset yourself. And I will give you several minutes, and you can let me know if you have finished. And if you have any questions, you can also let me know. Okay, I see a question. So for the condition object you created, you know how many were in treatment versus control groups because it is a smaller data set. If we had larger data set, how would you approach it? So for large data sets, usually the data set will come with a condition vector itself. So when I did the analysis myself, for most data sets, the condition will be part of the data set. So I think for the, if you are using, I'm not sure whether you do bulk analysis or single cell analysis. If you are using single cell analysis, the single cell object, the single cell experiment object itself have the metadata part, and that will usually include the cell type information. And if you are using the analysis on bulk RNA-seq datasets, their datasets, their matrix will often come with a condition label. vector. And that vector will include the treatment and control information for each of the samples. And you can use that vector as the condition here. Is now all betas equals to 0? Okay, thank you for your question. The null hypothesis here depends on what we are looking at. Here we only have one predictor, which is the conditions. So it does not matter whether we are interested in one predictor or all predictors, because we only have one predictor here. But if we have multiple predictors, and the t-test, sorry, the p-values here are only for one predictor. So if you want to know whether all of the predictors are equal to 0, you may need to use another test, for example, using the ANOVA. And yeah, and that will give you the results, the F-test results, which test whether all the betas are equal to 0. But here we only have one predictor, so the test is on this single predictor, and the p-value is from the hypothesis testing whether the coefficient for this condition predictor is equal to 0 or not. Okay, so yeah, so if you have not finished these, you can continue, and please let me know if you have done. Okay, thank you. Okay, thank you for your response. So if you have finished, we can go to our next question. So far we have know how to calculate the p-value for one of the genes. And next question is, how can we calculate the p-values for all the genes? And what will be the distribution of the p-values? So yeah, finish this. If you have finished the first part, so the next question is how to calculate the p-values for all genes, and what's the distribution of p-values. So just remember that we have 200 genes for this problem. So we may have to calculate p-values for 200 genes. So I will give you 1 minute to think about this. And if you find a solution, you can try it yourself, and I will introduce how to do this later. Okay, so if we have multiple genes and we are interested in calculate all those p-values, and we can use a iteration to calculate these p-values one by one, and it is called marginal test in high throughput data analysis, because we are interested in testing the genes one by one. So we can first generate a vector called p-values to be used to store the p-values for all the genes. We can make it web 0 to 100. So we have 200 genes, so we need 200 p-values. And we can have a for loop for I from 1 to 100 for each of the genes. We just do repeat what we have done. So we first generate look at the i's column of the data frame, which is the i's gene, and then we still use this condition label as our predictor. So as it is the same for all the genes, we can make it out of the iteration. And then we can generate a data frame combining the count and condition, and we can run a regression model, GNN model, to do the the Poisson regression, and then we can get the p-values. So okay, so I'm not sure where the model by itself has the p-values. Okay, note. So we still need to do model summary equals to the summary of the model, and p-values I will be equal to the model summary coefficient. So it will be, so if we look at the coefficient part of the summary of the model, we will see that it has 2 rows and 4 columns. And the second row will be about the predictor of interest, and the fourth column will be the p-values. So we will get the second row and the fourth column of this matrix, and we will store it as the p-values. Sorry, maybe I missed it. Is there a reason for choosing Web 200, or is it random? It is not random because we so first, this part is not random. We want to have a vector with length equals to 200, because we have, if we look at the number of genes, we look at the number of columns of the simul count matrix, we can see that it has 200 columns corresponding to the 200 genes. So if we want to calculate the gene, for each gene, we want to calculate the p-value, we will get 200 p-values. And we want to use this vector to store the results of the p-values. So we also need a vector with length equal to 200. And for the first part, so here I just want to use this one to generate a vector of zeros and modify the values one by one by doing the regression. So I think you can change this number to anything you like. You change it to an age or 1 or 0, or they're all good, but yeah, just make sure that. Oh, okay, yeah, okay, I see. And then for each of the genes, we get the model summary, and we use these to get the p-values out of this matrix. And then we can save this p-value to the ith entry of the vector, and then we can run this for loop, and then we will get 200 p-values. So let's look at what these 200 p-values look like. We can use the haste function to generate the histogram. And this will be the histogram. So we can see that for some of the genes, they are DE genes, so that the p-values for those genes are quite small. And for the majority of the genes, they are non-DE genes. So that their p-values come from a uniform distribution, uniform distributed from 0 to 1. So it is the case that I mentioned before. If we use the correct model, the p-values will be uniformly distributed from 0 to 1. And for this part, the part which is greater than the uniform distribution, this left peak or left tail, it is for the this is for the DE genes identified. So this will be the distribution of the p-values. And this is how we calculate do the DE analysis for this matrix. And actually in application, in most cases, you do not need to do the regression yourself. There are a lot of softwares for DE analysis, for example, HR and DSeq2. And I think there are also some workshops about how to do DE analysis using those softwares. Yeah, I want to introduce it in the regression, using the regression model myself, because I just want to show that how these softwares works and how those regression models can be used in reality. And it may also help if you want to design your own softwares or methods yourself. Okay, let's come back to the slides. So we have finished this. We have calculated the p-values for all the genes, and we can see that there are some DE genes from this dataset. However, the Poisson regression model is not always the best for the count data, because there is an important property for Poisson distribution, which is that the mean and the variance are the same for Poisson distribution. And for real data, it may not be the case. And we find that from a lot of literature and real data sets, we find that for real gene expression data sets, the variance is often larger compared to the mean. And we call this over dispersion. So here, over dispersion means that the data is more dispersed than expectation, and it has larger variance compared to the mean. In this case, we cannot use Poisson distribution as our model anymore. And there is an alternative called negative binomial distribution. So here we change the format from yi follows a Poisson distribution into this format. That is, yi follows a negative binomial distribution with mean equals to mu I. And we have an extra theta, which is a dispersion parameter. So this parameter will describe how the variance is larger compared to the mean. So here the mu I is the mean parameter. So if yi comes from this distribution, the expectation of yi is still mu I, but the variance of y will greater than mu I. Similar to Poisson distribution, a random variable from a negative binomial distribution is also always non-negative integers, which make it a good fit for the read count data. A property of negative binomial distribution is that if a random variable comes from a negative binomial distribution with mu parameter equals to mu I, then the expected value is value is mu I, and the variance of yi will be mu I plus mu I squared over theta. So here theta is the dispersion parameter. So we can see that if theta is very large, so if theta is very large, then the variance will be similar to the expectation, which means that in this case, it is more like a Poisson distribution. But if theta is very small, then the variance will be much larger compared to the mean. And this time, in this case, we have very large dispersion. So it is how this dispersion parameter works. It will change the shape of the negative binomial distribution. And in you may see different definitions of the dispersion parameters in other papers or in other class, because we don't have a universal definition for the Nielsen binomial distribution. We may the dispersion parameter may take different formats. Sometimes we call it size, sometimes we call it probability. We have different ways to call this, and they may have different different formats. But we just need to remember that the Nielsen binomial distribution has larger variance compared to the mean, and there will be a dispersion parameter which controls that kind of dispersion. Okay, if you are not so familiar with the Nielsen binomial distribution, we can just generate some random variables to see what this distribution look like. So I just add this part here. So I would like to use this function Rn binom, which means random values from Nielsen binomial distribution. So Rn binom to generate Nielsen binomial random variables. And I will show what the distribution look like, and I will compare it with Poisson distribution with the same mean. So let's come back to the R, and I will just give you a brief idea of what Nielsen binomial distribution look like and how it compare with Poisson distribution. So maybe you can first generate some random variables from Poisson distribution. So we use, okay, we make A equals to RPOI-ish. You can generate 1,000 values from Poisson distribution and make the mean equals to 10. And we can use here's a function to generate the histogram. Here's A. We can also generate random variables from Nielsen binomial distribution. We also generate 1,000 values, and we make mu equals to 10 to make sure that these two distributions have the same mean. And we also have an actual argument called theta. I'm not sure whether they call it theta in R. I guess so. So we make theta equals to 1. It means that the variance will be 10 plus 10 squared over theta, which is more than 100. So it will be very large. So then we can also generate a histogram for the Nielsen binomial distribution. Let's run this. Okay, sorry. So the in R, it is not called theta, but no problem. I guess it is called size. Yeah, it's called size. So sometimes it is called size, and we generate it from that function, and let's see what the data look like. So let's first look at the histogram of the Poisson distribution. So we can see that the shape looks very similar to a normal distribution, but the only difference is that it has all the values are integers, and we can see that we have most values are greater than 5, or between 5 and 15 within this small range, and they are centered around 10, which is the mean. However, if we look at the Nielsen binomial distribution, we can see that we have some very large values. We have values greater than 80 even, and the majority of values are between 10 and 0. So we can, if we compare these two shapes, you can see that the Nielsen binomial have much larger variance. It may have very large values given the same mean compared to the Poisson distribution. So you can see for Poisson, the largest value is only 20, but for Nielsen binomial, you may have very large values. The shape may be monotone decreasing, so we have a bell shaped for this Poisson distribution. So we can see that these two distributions are quite different, even though they are all distributions for counts. So if you want to use one distribution for your data set, you need to carefully check the distribution of your data set to compare it with Poisson and Nielsen binomial to see which one fit better. And that will affect the performance of your model a lot. A correct model is always much better compared to a wrong model. So here I just want to show how these two distributions look like, and you can see that they are very different. Okay, so similar to the Poisson distribution, Poisson regression models, we want to make sure that the response have the same range as the predictor. So we want to make sure that the left-hand side is also from negative infinity to positive infinity. So we also take log of the mu I to make it the linear combination of the predictors. So this will be a formula, and it is very similar to the Poisson regression. Okay, this is about the theories, and we would like to introduce the application of this negative binomial regression model. So to use this model, we may use the MASS package. I think we have already used this package in our first workshop. So I suppose you have already installed this package, and we will use a function called glm.nb to do the negative binomial regression. And the formula is just very similar to the LM function. So we still need to write the formula of the regression model, and we will also need to name the dataset we are using. And this function will estimate the dispersion parameter theta first, or the science fact parameter. So we can see if we go back to the formulation, there's theta, the distribution parameter is the same for all the observations, for all the eyes. So we don't see a subscript I because it is fixed and it will not be changed for different observations. So for different I, the theta is the same. And the function will first estimate the theta and then use the estimated theta to do the regression. And it is how it works. And we can go to the CAS04 dataset to see how we can use this model. So we will first look at the CAS04 dataset, and we want to use the number of cylinders to predict the horsepower. So the reason for this is that if we look at the horsepower, you can see that CAS04 horsepower. When we look at the distribution of the horsepower, we can see that it is clear that has larger variance compared to the mean. So I think it is an over dispersed data set. And this data set, all the values in this data set are all integers. And that's why I also would like to make it the response. And yeah, we can use this function GIMNB to do the regression. So before doing the negative binomial regression, we can try using simple linear regression to see why we don't prefer that one. So I would like to use simple linear regression first and put regression line to see whether it is a good regression model. And let's do this. So I think for the simple linear regression, you have done this a lot of times. So I can quickly finish this myself. I will do model 1, which is linear model. And this will be response is horsepower. And the predictor will be cylinders. And the data set is CAS04. Okay, and we can use the scatter plot and regression line to visualize the regression results. So we can first plot horsepower versus cylinders in a scatter plot. Okay, this will be the scatter plot, and if we do the regression line, so this will be we can make use lines function to generate line, and the x-axis will be the number of cylinders, and the y-axis will be the horsepower. Would you mind scrolling up for a second to the looping code for generating Poisson regression p-value histograms? Okay. Is this? Okay. Do you mean this part? Okay. Yeah, I think I will upload the code and the slides and videos so that I think you will not miss these things. Okay, so have you finished? So once you have finished, I will go back to, okay, thank you. Okay, let's go back to the hash datasets. So lines, so if we want to add a line to an existing plot, we can use the lines function. So we can lines cast their four cylinders, and the y-axis will be the fitted value of model one. So it will be model one fitted value. And we can get the regression line. Okay, so it seems that the dataset looks good, but you may find that the shape for if we don't look at this data point, you may find that most dots is above this regression line for the small x, especially for x equal to 5, then we can see that all the dots are above the regression line. And for it's also the same case for these. So if you are not pretty sure about this, we can look at the you can also look at the diagnostic plot. So we can see that if we look at QQ plots, they are over the diagonal, which means that the model assumptions are violated. And we can also see increasing pattern in the scale location plot. So, and okay, not so bad an outlier, but still the model assumptions are violated. So we can see that the linear regression model may not be a very good case here, and you like to use negative binomial model here as another alternative. So how to use the GLMNB? So we can just use that in similar ways as linear model. So we just copy this, and we only need to change the LM into GLM.NB, and look at the results. So from the GLMNB, we can also see similar conclusions from the Poisson regression. We will know the p-values, the estimate coefficients for the predictors, and we will also get the p-values for the predictor. And we will also have the results for the estimated dispersion parameter for the theta for the negative binomial model, and we can use these results to make some inferences. We can also use the line function to generate a regression line. So we need to make x-axis still equals to the cylinders, and the y-axis to be the model 2 fitted values. And remember here we need to use some sorting to make sure that the results look good. And we can change the color equals to green to make a green curve. And you can see, oh, okay, sorry, I made a mistake. Okay, I didn't make a mistake. That is correct. So we can see that in this time, we will have a exponential trend instead of a linear trend from the x-axis and the y-axis. And this exponential trend may have, okay, so we still have the 5 dots above this line. So the problem for the that I described maybe still exists, but maybe you can look at the diagnostic plot. So if you look at plot of the model 2 to see whether this will increase the properties for the QQ plot. Okay, so maybe the results didn't improve a lot. So we can see that those dots are still above the regression line, and the normal arrow assumption is still violated. But we may have a better scale location plot to show that the residuals are within the same scale. That's something that has been improved. But if we look at the QQ plot, we do have some improvement. It's better than linear model, but still not so good. So I have to apologize to you that this example that is so good. But yes, I may like to change the horsepower into suggest retail price if you are not so you do not mind, to better show how it's improved the model. Suggest retail price. Okay. Sorry for this. I will change this into suggest retail price. And now I will modify the slide later. So I didn't use the base example here, and I will do this. Okay, so what happened here? And let me figure it out. Okay, it seems to be not a problem. So maybe I need to do the sorting. I don't know, or it will be some problem. Okay, it still doesn't work. Let me see whether this one works. Okay. Also does not work. Plot new has not been coded yet. Yeah, I think I will figure it out later. Sorry for this, but here we go. So maybe we can still go back to the previous example using horsepower. So here I just show how to use the gim.nb functions, and maybe you can go to our next example. So this time we can still repeat the D analysis. For the DEG analysis, we are interested in finding the genes which are differentially expressed between the two conditions. And we have already shown how to do this using the Poisson regression. So this time we are interested in solving this problem using the negative binomial regression. Let's go to another simulated count matrix, which is called simulcount MB. This is another matrix I have sent to you. And for this data set, I generated some random counts from negative binomial distribution. So these counts are more as higher variance. And we can see how we can improve the performance of the DE test if we change the model from Poisson regression to negative binomial regression. So in this data set, each row is still a biological sample and each column is still a gene, and the entries are read counts. And for the first gene, we can use negative binomial regression to predict the count using the condition. So we can see that here we are doing things which are very, very similar compared to the previous analysis. So if you don't mind, I will just copy all the codes and repeat it. Okay, so here the first thing that we changed the name of the dataset from simulcount pause to simulcount MB. And then for the first gene, we can still create vector for the read counts, and for the second, then if we look at we may name it as simulcount 2, so that we have a separate matrix, which is different from the previous one. Okay. So we still make if we look at this matrix, we can see that we still have 5 treatment samples and 5 control samples. And if we look at the numbers, we can see that for the first gene, we have some very large values. And this is because of the existence of overdispersion. So it means that we may have some extremely large values for some of the samples because of the dispersion. And okay, so first we will have the count for the first gene, and we will also have the condition vector for that gene. And we can combine these two things together, and we do this test by using the gm.nb function, and we don't need this family argument. Okay, so for the first gene, we have done the test. We compare the we will try to use condition as a predictor to predict count to see whether count is related to condition. And after the regression, we can see that the p-values for this gene is 0.02, which is smaller than 0.05. So we get a significant result. And we will say that this gene is a D gene from the negative binomial regression. And we can also use a for loop to calculate the p-values for all the genes. So first, we can still use similar procedures. First, generate a vector of 200 p-values, and then for each of the gene, we get the count of the gene for the X gene, and we get the data frame and use gm.nb to run the negative binomial regression on that data set. And then for that gene, and then we save the values, save the p-values from this negative binomial model. Okay. And I want to make sure that everything is the same for negative binomial model as for Poisson regression model. So we can run this, and we can, okay, we make it some warnings for the negative binomial regression. It is very common because it will have to use iterations to estimate the values of theta. So in this procedure, it may have some warnings because of the scale of some of the reads. So here I just keep these, and we just don't need to worry about these warnings. And then we can also look at the histogram, the p-value, and we can still see the similar patterns. We have some genes which has very small p-values, but for the majority, the p-value seems to have a uniform distribution from 0 to 1. So we just repeat everything we have done for the Poisson regression, but on another data set, but using negative binomial regression. So I think I will give you several minutes to repeat these procedures on your own, and we will also have a 10 minutes break after this. So we will come back at 5:43, and we can first try to repeat these negative binomial procedures to the D analysis, and you can also take a rest after that. I will stop recording here. Yes, thank you so much. Okay, so I may need to do it again. So for the so then we like to evaluate the results of the DE analysis. So as I generate the data set myself, so I know which of the genes are true DE genes. For the true DE genes, I generate the counts from the two conditions using two different distributions with different means. So they are true DE genes. And for the last 160 genes, I generate the read counts from the two conditions from the same negative binomial distribution. So I know that all the difference in the counts are totally from random error, and they are actually non-DE genes. So as we already know which of them are true DE genes and which of them are true non-DE genes, we can call DE gene as a false discovery if it is identified as DE gene, but it is actually not a true DE gene. So in this case, it is a discovery, but it is a false discovery. So if we use 0.05 as the threshold, for example, if we think a p-value smaller than 0.05 as a DE gene and a p-value greater than 0.05 as non-DE gene, if we make it the threshold for our discovery, we can compare the results for these two regression models. So if we use Poisson regression models, let's see how many false discoveries do we have. And we will also see that if we use negative binomial regression, how many false discoveries do we have? So maybe we can start from the negative binomial regression because we have just done this and we already have the p-values for all the genes, and we just need to compare the p-values with 0.05 and to see which of their genes have p-values greater than 0.05, and to see how many of them are actually non-DE genes, and those will be the false discoveries. So maybe you can do it yourself first. So for the NB regression, we have already finished all the analysis so that we will have a vector of p-values. So from the p-values, we will make the 0.05 as threshold, and then we can see which of the genes have p-values greater than 0.05, and let's compare our discoveries with the true DE gene list and to see how many false discoveries do we have. And I will give you 3 minutes for this. And after this, I will go to the Poisson regression results. So to calculate the number of false discoveries from this DE analysis. So has it anyone finished? Yeah, I will wait for 1 more minute. Okay, Philip says he gets 40, 45 DEGs. And how many of them are false discoveries? How many of them are DEGs which are actually non-DEGs, but identified as DEGs? Because we already know that the first 40 ones are true DEGs. So you can look at the index of those genes to see how many of them are having indices greater than 40. Okay, I can do this together. So first, let's look at the p-values. How many of them are greater than 0.05? So the D genes. So we can count the number of discoveries by looking at the number of p-values which are smaller than 0.05, which is our threshold, and it will be 45, which means that the Philip get very good answer. And we can also count the number of p-values. So we look at the indices of the p-values which are smaller than 0.05 to see how many of them are false discoveries. So let's have a brief look first. So we can see that we have some of the p-values which are from first 40 genes that are, which means that these are true D genes. But we also have several genes which are identified as D genes, but they are from the last 40. And it means that these are false discoveries. And we can calculate the number of these vectors which are greater than 40. And we can see that we actually have 24 false discoveries. So which means that among the 45 discoveries, 24 of them are false discoveries. So do you think it is a very large proportion? Okay, this is for the nicotine binomial regression, and we can do similar things for the Poisson regression. And that results will be even more interesting. So if we just copy these things, but we just change the, okay, maybe you can name it p-values 2. P-values Poisson. It may be Poisson regression. P-values Poisson regression. And we still have the same format, but we change this part into a Poisson regression. So we only need to change this part, change the model from nicotine binomial regression into Poisson regression. And then we can repeat everything and we calculate the number of discoveries and the number of false discoveries. Okay, let's do this. So first generate the p-values and then calculate the number of p-values smaller than 0.05. So first, okay, oh, sorry, my bad. I forgot to change the, I made a typo here. We had do the copy paste thing. Okay, should be some which this smaller than 0.05. Okay. We can see that the number of discoveries is as large as 142 for the Poisson regression. You only have 200 genes, and almost all the genes are identified from Poisson regression model. And 114 of them are false discoveries, which means that the majority of the discoveries are false discoveries if we use the Poisson regression. So what conclusion can we make? So for both seeing, if we use p-value threshold as a threshold for discoveries, we will all have a large number of discoveries which are false. It makes sense because, as we have already shown, that if we look at the distribution of the p-values, I think I still have that figure. Do I have that one? Oh, maybe I have. Okay, let me draw the figure again. Okay, if we look at the histogram, we can see that even for if we use the correct model, if we use the negative binomial model, we can see that for the non-DE genes, the p-value are uniformly distributed from 0 to 1. And it means that if it is uniformly distributed, it means that even for non-DE genes, it also has a chance to have p-values more than 0.05, and that probability will exactly be 0.05, so that we will be part of the discoveries which are actually false discoveries. It makes sense. But if we compare the results from negative binomial regression to the results from the Poisson regression, we can see that the number of false discoveries is totally in different scale. If we use negative binomial regression, the number of false discoveries is still okay, not so large. But if we use the Poisson regression, we can see that the number of discoveries is too large, and the number of false discoveries is also too large. And this is the effect of using an incorrect model. So here we know that all the data points, all the counts are from negative binomial distribution. I know it because I generated data myself. And I know that using Poisson distribution is incorrect because I know the data is not from Poisson distribution, so that we can know this. We can know that if we use the incorrect model, if we use Poisson regression model, the results will be totally bad, and the number of false discoveries will be very, very large, and we should always try to avoid such problems. Okay, what if you reduce the p-values to smaller than 0.01 for the two models? Yeah, I think we made a very, very, very nice point, and that's something I would like to discuss later. And we can have a look to see what the results look like if we change the threshold from 0.05 to 0.01. So first, for the negative binomial regression, the number of p-values more than 0.01 is only 28. So we have a reduced number of discoveries. And then we look at the number of false discoveries, it also decreased. So we will also have a decreased number of false discoveries. And for the Poisson regression, we change, so we use 0.05, we have 152 discoveries, and we change it to 0.01. The number doesn't decrease a lot. And we still change it to 0.01. You can see that the majority are still non-DE genes. So we can see that. So we can see that if we reduce the number, or if we make the threshold smaller, it is true that we have smaller number of discoveries and false discoveries, but it seems that this threshold is not small enough to make sure that we have no false discoveries or have a small proportion of false discoveries. To make it smaller, we may need a smaller threshold. So we can try something else. For example, make it the threshold 0.001 to see what happens. So if we make a threshold 0.001, and we can see that this time we only have 9 discoveries, and we still have 6 false discoveries. So the proportion is still large, and it still does not totally solve our problem. So we can see that still a large number of false discoveries here. So we may need to further reduce the threshold if we want to control the number of false discoveries. And that's something that I would like to introduce it further. Okay, so yeah, thank you for your question. And yeah, we both see that the problem of false discoveries is very important problem here, and we need to solve it. Okay, then let's go to our next slide. Okay, this is about 2 important concepts for evaluation of the results. So there are 2 important amounts. One is called false discovery proportion, which is called which FD short for we use FDP short for false discovery proportion, and it is defined as the number of false discoveries over the total number of discoveries. And there is another quantity called power, statistical power, which is the number of true discoveries over the number of true DE genes. So if we hope our results to be good, we hope that among our discoveries, the proportion of false discoveries is as small as possible. That's something we design. And so we want to have a small FDP. And we also want to make sure that we identify as many true DE genes as possible. So the power is the number of true discoveries over the number of true DE genes, which is the proportion of true DE genes identified by the test. So you want to have a small FDP, but a higher power. So these 2 quantities are used in different analysis to describe how well our results is. And we can calculate the FDP and power for our results. So if we use the Poisson regression, what's the FDP and power? And we use negative binomial regression, what's the FDP and power? So we can do these calculations. So here we still use the 0.05 threshold to make it consistent. And let's see. Okay, so let's just to make sure that our results are good, and the FDP can be the proportion of false discoveries, which will be the sum of this false discoveries, number of false discoveries over the number of total discoveries. So this will be our FDP. So, and we will also have the power. the power will be the number of true discoveries. So it will be the number of p-values. So which of the discoveries, so this will be our discoveries, and we want to see which of discoveries are true discoveries. And the true discovery will have indices smaller or equal to 40. So this will be the number of true discoveries. And the denominator will be the number of total true D genes. So it is 40 here because the first 40 are true D genes from our definition. So we can also know the power. Okay, so this is the definition of FDP and definition for power, and we can calculate these two quantities. So the FDP is 0.5 and power is 0.5. So we can see that these two, so we don't have very large power and we don't have a very small FDP for this case. And we can do this for the for the Poisson regression in the similar way, and we can just change the p-values into p-values Poisson regression, which is the p-values from the Poisson regression. I just run it again to make sure that everything is correct. And so that we can see the FDP is 0.75 and the power is, oh, sorry. P-value, okay, I have extra S here. So, and the power will be 0.95. So we can see that. So you can see that if we compare these two regression models, the negative binomial regression will have smaller false discovery proportion, but smaller power. If we look at the Poisson regression model, it has very large power, but it also has very large FDP. So these two things are, we can see that there is a trade-off between these two things. In most cases, if we want to get higher power, we may lose the control of the number of false discoveries. But if we want to control the number of false discoveries, we may lose power. So these two things are in many cases, these two things are in contrary, and we need to find a trade-off between these two things. However, if we look at the Poisson regression model, you can see that about 3/4 of the discoveries are false discoveries, and we can see that if we identify the G gene from this test, we can never believe the results. So it doesn't, even it has very large power, we don't think it is very good method, because if we predict all the genes to be D genes, we will have 100% power, but we also have a very large proportion of false discoveries, and that's not something we want. So we can go to our next part. So we can see that for both cases, so from these results, we can see this. Okay, we can first get some conclusions by comparing these two models. We may use the incorrect model to do the regression. For example, using the Poisson regression model for the negative binomial distribution, we may have more false discoveries. And these false discoveries come from model misspecification. And so we need to check the model assumptions, whether they are violated. The first way is to do diagnostic plots. So as we have done before, we can also, for the model from negative binomial regression and Poisson regression, we can also use diagnostic plots to see whether the assumption are violated. This is one way. And another way is to do greediness of fit test. And I will put it in the last part of the workshop if I have time. So we always need to check whether the model assumptions are violated before we decide to use a specific model. And if we use the correct model, even if we use the correct model, for example, we use the negative binomial model for the negative binomial regression for the negative binomial model, even if we use the correct model, we still have false discoveries. When the null hypothesis is true, we know that the p-values are identically and independently distributed from uniform distribution, and the probability that the p-value is more than or equal to 0.05 is 0.05. So it means that if we, in the D analysis, if we have 160 non-D genes, on average, even if the p-values are perfect, on average, we will still have 8 false discoveries when the model is exactly the correct one. And if we go to the negative binomial model if we go back to the negative binomial regression, we will see that here we have more false discoveries than expected. So we have the 24 false discoveries compared to the 8 discoveries, which is the expectation. So why is the case? It's because that for negative binomial regression, the theta is estimated from the model, is estimated from the regression model. And the estimation of the theta is not accurate, which means that if we do not have an accurate estimate of the theta, and in this case, we all still have a wrong model specification because we do not have the correct theta. And this wrong theta, even it may be close to the true theta, but if it is different from the true theta and have some difference, we still do not have the correct model. And it is why, in this case, even if we still use the negative binomial distribution to describe data set, but if we use the wrong theta, we still have the problem with model misspecification. And that's why we should always be careful when using the negative binomial model, because using this, whenever we use this, we have the risk of model misspecification, and we may have inflated number of false discoveries. And we should keep it in mind, because many popular tools, including DSeq2 and HR, those methods use negative binomial regression, and we find that these methods will lead to large number of false discoveries. Okay, let's some interpretations about the results, and let's think about how to solve these problems. Oh, okay. First of all, we need to identify. I would like to mention why we need to solve the problem. Why we want to get rid of those false discoveries. The identifier D genes from the D analysis will be subject to downstream biological validation. So we will do experiment to see whether these genes do have some biological functions that are related to the condition, for example, disease or the cell types, these things. And these experiments will cost money and labor. So we want to save these things because we don't want to waste a lot of time, a lot of money. From the previous analysis, we see that if we set the p-value threshold alpha to be 0.05, it may lead to too many false discoveries. And we may like to control the number of false discoveries, and there have been many criteria proposed to describe the quality of the discoveries. And we have two most widely used criteria. The first is called family-wise error rate, and the second is called false discovery rate. And I would like to introduce these two criteria one by one. Okay, the first one is called family-wise error rate. Family-wise error rate aims to control the probability of having any false positives. And from the definition, we can see that family-wise error rate is the probability that any of the tests are false positives. So we can see that the probability that any of the tests are false positives is smaller than the sum of the probability that the i's test is the false positive. I from 1 to n. So we can see that if we have m different tests, then the family-wise error rate will be smaller or equal to n times alpha. So it means that if we set alpha equal to, if we set the threshold alpha equal to 0.05 over n, then we can have family-wise error rates under control so that we can make sure that the probability of having any false positives to be smaller than 0.05 if we change the threshold from 0.05 into 0.05 over n. So the procedure, the detection procedure can be just comparing every p-value to this 0.05 over n and rejects the i's null hypothesis if pi is smaller or equal to 0.05 over n. And we call this procedure Baffaroni procedure. And if we want to use R to implement this procedure, we can use the function called p.adjust, and this will help us to do the p-value adjustment. And as I just said, for the negative binomial distribution, even if we use the correct model, we still have the problem of using the incorrect theta. So let's come back to the simul count Poisson dataset. For this dataset, all the values are from the Poisson distribution. So the Poisson model will be a good fit here. And we can see that if we use the correct model and if we calculate p-values, what if we use the Baffaroni correction, and we can see how many false discoveries left. Okay, let's go to the first data set. Okay, so let's start our p-value correction task. Okay, so this time we will go back to the simul data. We'll go to the Poisson regression, sorry, the Poisson distributed dataset. And we would like to calculate the p-values for each of the genes using Poisson distribution. So let's go to just copy this and change the dataset from simul count 2 to simul count and get the p-value vector, and we can calculate the FTP in this case. Okay, so we can see that if we just if we just use this procedure but change the dataset from simul count 2 from the second simulated dataset to the first simulated dataset, then we will have a much smaller false discovery proportion. And let's try our idea of using p-value adjustment. So we would like to adjust the p-value, adjusted p to be the p.adjust p-values, sorry, p-values and method equals to Baffaroni. I may forgot how to spell this, so I will need, okay, Baffaroni. So this name is too long, so I may need to search for this. Okay, Baffaroni. Okay, so you can, if you cannot remember how to spell this long word, you can also ask. Okay, I see a question. Is Baffaroni a better correction method compared to BH correction when analyzing these regression models? Yeah, I think you made a very good point, and I will compare these two methods later. I will first introduce these two corrections one by one, and I will make a comparison between these two things as a summary. Okay, so for the Baffaroni correction, we can just use this way to get the adjusted p-values. And then we can calculate the FDP by make those genes which has adjusted p-values smaller than 0.05 instead of the original p-values. So that we just copy the formula for FDP and calculate it again. Okay, so we do the calculation and okay, I guess I made a mistake here. P dot adjust p values. Okay. Oh, I understand what happens. So I forgot, I made a mistake here. So it should be p value post ring. Yeah, I made a mistake. Okay, okay, then that makes sense. So this time we can see that the false discovery proportion becomes 0 after the Baffaroni correction. So we can see that after the correction, we only have okay, we have 40. We have 40 discoveries, and all of them are true discoveries. And that's how this Baffaroni correction works. If we do not do the correction, we will have false discovery equals to 0.21. But if we do the correction, the false discovery proportion will be 0. And yeah, that's how it works. So we can set a p-value threshold to be smaller so that we can have a more constrained threshold so that we will identify this and hopefully it will remove those discoveries which are identified totally by random effect. And that is for the Baffaroni correction. And maybe you can also repeat this procedure on your site and you can let me know once you have finished. So here we just need to calculate the p-values for all the genes using Poisson regression on the Poisson dataset and use this command line to do the p-value correction. So you can try it on your site and let me know once you have finished. Okay, I see Philip has finished. Okay, I will give you 1 more minute and I will introduce the next example. Okay, I think most of you have finished. Okay, and I will go to the next part first. So for the, okay, so this is for the some data set, and we can see that the Baffaroni correction has perfect performance. And what if we look at the negative binomial regression on the negative binomial data set? So here I just need to, I guess I just need to change the copy other codes here because they are exactly the same. Okay. So this here we are looking at the negative binomial data set and calculate the p-values, and you can see that the FTP is around 50%, and we want to control the FTP by doing the adjustment. So this time we can also do the p-value adjustment using this command. Adjust the p, adjust, okay, this is called p-values. I just copied here and adjust the p and b. Okay, and the FTP will be the sum of the adjusted p-values, which is smaller than 0.05, which this is the number of discoveries, and we look at the number of these discoveries which are true over the total number of discoveries. It is the FTP after the correction, and we can see that after, okay. Okay, so we can see that after the Baffaroni correction, so this time, yeah, I'm pretty sure that this time I didn't make any mistakes. Just double check. So p-values, the correct data set, correct. Okay. Okay, I think I didn't make any mistake here. I just do the correction on this p-value vector and get the just p-value, and we can see that for this data set, the false discovery rate is false discovery proportion is quite high. It is still very large. So what it tells us, so it tells us that, so if we use the negative binomial regression model, if we use that model, and which estimates the theta itself, the estimation accuracy of the theta may influence the results a lot. And in this case, after the correction, we only have 5 discoveries, and also, sorry, we only have 6 discoveries. We only have 6 discoveries, and 5 of them are false discoveries. And we can see that first, after the correction, we only have a very small amount of discoveries left. That's one problem with the Baffaroni correction. And secondly, that's the number of false discoveries is still very large because of model miss specification problem. So these together tells us that, yeah, we always need to make sure that we have the correct model. And if we do have model with specification, even after Baffaroni correction, the false discovery proportion can still be very large. And yeah, and that's something that we need to avoid. That's for the Baffaroni correction. You can see that one problem of this correction is that it's maybe too conservative. Sometimes with such a small threshold, we may have only have a very small number of discoveries left, and that's something that we don't want to see. And I'd like to introduce another criterion which can be used to describe the quality of the discoveries, which is called false discovery rate. The definition of false discovery is the expectation of FDP. So the expectation of the number of false positives over the total number of discoveries. So it is just expectation of FDP. Here we have expectation sign here because for different data sets, the false discovery proportion is not fixed. But we want to control if we do the random sampling many times, the expected FDP is smaller than a threshold. That's something that I like to control. And the procedure to control this is called Benjamin-Hochschild procedure. And this procedure is as follows. First, we order all the p-values from smallest to largest, so that we will have p parentheses 1s smaller than p parentheses 2s, and a lot of p-values and smaller than p parentheses n. So we order these p-values. So here p parentheses 1 is the smallest p-values among all the p-values, and this will be largest p-values among all the p-values. So we first do ordering, and then we will compare the i's ordered p-values with this ratio, 0.05 times I over n. So if, for example, if we can look at the smallest p-value, we will compare it with 0.05 over n, which is the same as Baffaroni threshold. But if for the second smallest p-value, we will compare it with 0.1 over n. So that's the difference between these two thresholds. And then we will reject the I's null hypothesis. We will reject the first I null hypothesis if p parentheses I is smaller equal than 0.05 times I over n. So that will be the procedure. And yeah, I think we can take a rest here because it is already 6:30. Yeah, I'd like to take a 10 minutes break here. And yes, as Eloy have just said, we can have, yeah. So we may need to have a workshop evaluation for everyone. So this is the QR code. So yeah. So if you would like to help me to evaluate this workshop, that will be very helpful. And thank you so much for joining this workshop. And you can scan this, and I think you will receive a survey, and you can finish the survey during this break. And yeah, I will stop the. Okay, let's go back to the false discovery rate example. So, okay, so we first introduced the Baffaroni correction, which just compares the p-values with a new threshold, 0.05 over m, where m is the number of tests or the number of genes in this case. And here we introduce another procedure called BH procedure, which first order the p-values and compare the ordered p-values with the new threshold. So now we can use the dataset to see how the BH procedure work, and we can still look at the simulcast pulse dataset and calculate the p-values for all the genes, and we can use the PHS function but change the method argument into BH to do the BH correction. And we can calculate the FDP after the correction. So let's go back. So this is how we did the calculate the p-values for all the genes, and this is for the Poisson data set, and we calculate the p-values, and we use the Baffaroni correction, and now we can do. Okay, this is so these are for Baffaroni correction. And now we would like to do BH procedure. So this time we will use method equal to BH to do the correction. And let's calculate the FDP. So here the FDP is still the number of false discoveries over the total number of discoveries, and it will be 0.09. So it is, so we can see that, yeah, it is. So the expectation of this proportion should be 0.05. But yeah, we will allow some randomness because if we do multiple sampling of the dataset from the same distribution, we may have different FDPs. And some FDPs will be large and some FDP will be small, but the FDR procedure or the BH procedure will control the expectation of the FDPs. So anyway, we can see that the FDP is small, and we still keep a large number of discoveries. So we can see the total number of discoveries. Total number of false discoveries is 4, and the total number of discoveries is total number of discoveries will be 44, I guess. Okay. So all the true discoveries were discovered, and we only have about 10% of false discoveries. So that's how the BH procedure on the Poisson dataset, and we can also try this on the negative binomial dataset. So in this case, we can do a JSP p-values method equals to BH. And okay, this time from the BH procedure for this one, we still have very large FDP because of model misspecification, but we have larger number of discoveries compared to the Baffaroni correction. For the Baffaroni correction, total number of discoveries was 6, but if we use BH procedure, the total number of discoveries will be 20. So we will have more discoveries, and we have larger number of discoveries and a smaller number of false discovery proportion for this case if we use BH procedure. Yeah, I mean, it may not be a very perfect case to show the theoretical property of these two methods, but yeah, but it somewhat shows that what if we use the wrong model? So both BH procedure and Baffaroni correction, these two may fail, and they may. But anyway, BH procedure will always give us more discoveries. So let's summarize the. Okay, so this is something that I have done. So we look at the simulcount MB dataset and calculate p-values, and look at the FDP and the number of discoveries. So I'd like to summarize these false positive control criteria. So to summarize, so we need these correction because we want to set a threshold on p-values, which is more strict compared to the original p-value threshold. If we do not have any consideration of the multiple testing, then the threshold will still be 0.05. But if we use familiarized error rate, the threshold will be 0.05 over n. And if we use the false discovery rate control, then the threshold will be the k's smallest p-value, where k is the largest integer, such that the first k smallest p-value satisfy that pk is smaller or equal to 0.05 times k over n. So this is the threshold for BH procedure. And in terms of the conservativeness, family-wise error weight control, or the Baffaroni procedure, is the most conservative one, and FTR control is in the middle, and the no consideration is the least conservative one. And in terms of the end of discoveries, it's just the reverse. So if we do not consider the multiple testing corrections, we will have the largest number of discoveries. And if we use FDR control, or if we use BH procedure, we will have a small number of discoveries. But if we use Baffaroni procedure, we will have a very small number of discoveries. And in many cases, that number can be as small as 0. So we can see that this is the comparison between these 3 methods, and we may need to make our choice depending on the data set or the analysis task we are looking at. So how conservative we need the discoveries to be. So if we don't want to see any false discoveries, then we should use Baffaroni correction. If we want the false discoveries to be small but not need to be exactly 0, then we can use the BH procedure. So that's how we make decisions. Okay, I think we have done this. So we can see that for the second dataset, for the dataset which comes from LinkedIn binomial distribution, if we use the wrong model, especially if we use the Poisson regression model, even if we do some multiple testing correction, there will be still a large number of false discoveries, and that's something that we don't want to see. And we can run it again to confirm this. So this is for the LinkedIn binomial dataset, and we can still calculate the p-values using the Poisson regression model, and we can do the p-value correction using BH procedure to see how many discoveries lived. So we can see that in this case, if we use the Poisson regression, even if we use the BH procedure, the number of discoveries is still very large. We have 150 discoveries. It's almost everything. And if we look at the number of false discoveries, we will have 112 false discoveries. So it means that if we use the wrong model, the results are not trustworthy at all. So we call this model miscertification, and you always want to avoid such problems. Okay, so let's go to our last part, which is about statistical rigor. So as we have just discussed, there has been many popular softwares proposed for the analysis. So we don't need to run those Poisson regression or LinkedIn binomial regression ourselves. So we already have many softwares, and they all have very nice well-written guidebooks, so that you can follow their procedures very quickly, including these 2 most popular methods called D6 and AGI. Both have been cited for tens of thousands of times. They are very popular. Both methods use LinkedIn binomial regression in their model, but they have some changes in the model part because they want to have a better estimate of the dispersion parameter. The dispersion parameter is a very important part, because if we do not have an accurate estimate of the dispersion parameter, we may have the problem model miscertification. So they improve that part to make their results more more reliable. However, even if they did such adjustment and try to make their models more reliable, we still have some problems with these softwares. And yes, and actually this is a paper that I published myself with my collaborators. And in this analysis, we look at a human immunotherapy dataset. And we have two groups of patients. One group was treated and one by therapy, and one was not treated. And so that we have two groups. So we have condition 1 and condition 2, and we can compare these two conditions and do D-analysis. And we can use these softwares which use negative binomial regression to do the D-analysis to identify genes that are differentially expressed between the two conditions. However, you would like to do a sanity check to see whether these methods have good performance on that dataset. And we want to check for false discoveries. What we did to check was we permute the dataset. So what do I mean by permutation? For example, we go back to the datasets that we have. So we will have the phi treatment and phi control. By permutation, it means that we just randomly permute these labels and do the analysis again. So it means that after permutation, the treat and the control information are just noise. So we actually, the label doesn't mean anything anymore. So that after the permutation, the two conditions will not mean anything because they are from permutation. They will not mean anything. And if we do the permutation and do the analysis again on the permuted condition, in this case, as the condition does not make sense anymore, the two new conditions, the two permuted conditions will not be useful to predict the counts, so that after permutation, all the genes should be non-D genes. So we do this on this dataset, and we want to see that if a method is reasonable on the permuted dataset, as from our expectation, that method should not identify any D genes. However, we look at the number of D genes identified on permuted data from D62 and AJAR, and we find that these two methods identified a large number of D genes on permuted dataset, which are these two bar plots, these two bars, and the two red dots are the number of D genes identified from the original dataset. So we can see that the number of D genes identified on permuted dataset is even larger than that from the original dataset, which indicates that the output of these two softwares may contain a large number of false discoveries. So let me show you, let me use our previous dataset to give you more intuition about what we have done. So let's look at the, oh, sorry, I should not need. Okay, so let me go back to the Poisson regression. Okay, so this is the Poisson regression model, and okay, stop here. So this is the dataset that we have been playing with, and let's stop this. Okay, okay, and we have the p-values as conditions, and what we did was to permute this condition vector. So So here the correct condition is first fire treatment and not fire control. This is the correct one. But after permutation, we can use the samples function to do a random permutation of this. So we can see that after permutation, the order of these 10 are totally random. So this condition is totally meaningless, and this is incorrect condition. And from this incorrect condition, we should not expect to see any DE genes. So we just repeat this. So we sample the condition and make it the condition for the regression. And we calculate the p-values for all the genes again. And we calculate the number of discoveries we use p-value threshold. So you can see that if we use p-value threshold, only 49 genes are identified. And if we use the BH procedure to do correction, so we will, okay, so this is adjusted p-value using BH procedure, and we can see what's the number of discoveries. Okay, so still for these three, so it's not. Let me just double check whether everything is correct. Okay, so okay. Oh, I guess I made some mistake. Okay, no, let's just do this again. Okay, so we have 33 p-values more than 0.05, and then we do BH procedure. P-values for 3. Okay. Okay, we can see that the number of discoveries will be very small. And this number will be much smaller than the original if we use the original data to do permutation. And we will see that if we increase the sample size, if we have much larger sample size, we will expect to see 0 discoveries if we use the permuted condition. That's what we find. And however, we find that if we use these two methods, D62 and Edge, they actually identified a large number of DE genes from the permuted data set. And this indicates that many of them are likely to be non-DE genes. And then we look at why this happens, and we check whether the model specification problem exists for this data set. And we find that it's true. So here, what we did was to do a goodness of fit test to test whether the negative binomial regression, the negative binomial model was fit. So if the p-value is small, it means that the model was not well fit. And the p-value, if the p-value is large, it means that the model is good. So here we find that if we compare the genes that are identified as DE genes from permuted datasets and other genes, you can see that for those genes, for these genes, which are frequently identified as DE genes on permuted datasets, they have smaller p-values. So these here, the y-axis are negative log p-values. So if this is larger, it means the p-values are smaller. So we can see that for those genes, for these genes, their p-values are smaller, which means that they do not have a very good fit for the negative binomial model. And that may explain why we have so many false discoveries. So let me show you how we can do goodness of fit test here. So a simple way to do goodness of fit is to use the function called ks.test. For example, if we first generate a random variable a, which are from the Poisson distribution, we generate 1,000 Poisson distributions with lambda equals to 10, and we have a random variable another random variable b, which is also from Poisson distribution. You can use KS test to see whether these two are from the same distribution. And we can see that the KS test tests the result p-value is 0.01. So you may think that this p-value is not is very small, but if we make b, for example, from negative binomial distribution and theta equals to 1, mu equals to 10. So if, however, we compare the negative binomial distribution with Poisson distribution, we will see that, okay, sorry, size equals to 1. And this time we do case test again, we can see that this p-value will be very, very small. So we know that if the two distributions are similar, the p-values from the KS test will be larger. And if two distributions are quite different, then the p-values from the KS test will be very small. So that we can use this to test whether two distributions are similar. So what we did was to test whether the counts for each gene is similar with the estimated negative binomial distribution from the model. And so that a small p-value indicates that they are not a good fit. And we find that for these genes, which are frequently identified as D genes on permuted dataset, these genes have smaller p-values, which indicate that the negative binomial model does not fit for those genes. And this will lead to smaller p-values, and this will further lead to large number of false discoveries. And what will be the so I don't know why this happens. Okay, sorry, I didn't know why, but yeah. But maybe we can just focus on this plot. It doesn't matter, and we can ignore the other parts, but only focus on this panel E. Yeah, I didn't check. I checked the PDF yesterday. It was fine, but I don't know why it becomes this here. Yeah, but if we just focus on the panel E here, what this did was to just look at the enriched biological pathways, which are related to those false D genes. So these genes are identified as D genes on permuted dataset. So they are definitely false discoveries. However, if we do some downstream analysis, for example, the GO analysis, which aim to identify some biological functions which are related to those genes, can find that we can still identify some biological functions which are related to those false discoveries. And some of these biological functions are even related to immune. And from these results, researchers may have questionable conclusions. From these results, they may think that these results validate that those genes are biologically meaningful. They are related to immune, so that it indicates that this immune therapy may have some influence on those important genes, and that genes may change the therapy output, and they may believe that though their therapy may be actually useful. However, all the D genes are false D genes, and their biological conclusions can be totally wrong from the incorrect discoveries. And that will be a very bad result if we do not pay attention to the model misspecification problem. And what should be the fix, and how can we solve this problem of model misspecification? One way to solve this is to use some general statistical methods which are not so reliable on the distributions of the count. because when we use regression models, we always have assumptions. And those assumptions can be violated in real data analysis. But however, there are some statistical methods which do not need such assumptions. For example, the Wilcoxon-Rexham test here. So if you are not so familiar with this test, it is a non-parametric test, which means that it does not have any distributional assumptions. It will test whether two random variables have the same median. And in R, we can simply use this Wilcox test function to do the test. So if we go back to our problem and go to the Poisson dataset, and yeah, let me show you how can we use Wilcoxon test to calculate p-value for each of the genes. So here we use this data set and still generate vector p-values, and we use the correct condition label, and we can, for each of the gene, we can also have count and data set, and here the thing that we change this into Wilcoxon test, and it will be the Wilcox output. So if we look at what it looks like, it will include the p-values from the test and also the test statistics, so that we can make the okay, maybe we can change the name of the output, okay, and equals to the p-value, okay, equals output. Okay, a typo. Okay, this is how we can use Wilcoxon test to calculate the p-values for each of the genes. This is another way to okay, we can see a lot of warnings because these tests will have some warnings when we have ties in the numbers, but it's okay. It will still calculate the p-value even when we have ties. And we can also do the adjusted p-value from BH procedure, and okay, and we can calculate the FTP. Ah, okay, so there are some NAs from the results. Okay, BH. Okay, so adjust p Wilcox. Okay, so you can see that as this is a problem Wilcoxon test, but I think if we change the threshold to 0.1, the results will be totally different. So if we set the threshold to be 0.1, then we can see that the false data proportion is quite small and it is smaller than 0.1. But if we set it as 0.05, we can see that the smallest p-value from the Wilcoxon test is 0.055, and it is greater than 0.05. So this is problem with this method. That is, when the sample size is small, we cannot use this method because it doesn't have power. But when the sample size is large, it will have larger power. And when we have enough sample size, we show that in this case, for example, in this case, when we have 51 samples from one condition and 58 samples from another condition, in this case, the Wilcoxon test will be very useful because first, it does not have any model assumptions, so it will not have the problem of model misspecifications. So it will not have the problem of false discoveries. And second, when we have a large sample size, the Wilcoxon test will also have good power. So it may also have good performance in that case. So, okay, so we can see that we have already used the Wilcoxon test to calculate p-values for the Poisson dataset, and we show that if we increase the threshold to 0.1, if we let FDR threshold to be 0.1, it can control the FDR and have good power. But if we use a smaller threshold, it loses power because that is the property for Wilcoxon test when the sample size is small. So to summarize, the main point for the above example is that when we are using regression models, we should always pay attention to the model misspecification problems. Or if we use those popular tools, we should always pay attention to the model misspecification problems. And one way to check whether each method works is to use permutation to do sanity check as we have done before. So if a method identified a large number of DEGs on the permuted dataset, it means that this method may be problematic on the original dataset. And it is likely that there are a lot of false discoveries. And second, if we already have large sample size, we can consider using non-parametric tests, for example, the Wilcoxon RAGSUM test. So it will not have the problem of model misspecification, and it will also have enough power when sample size is large. And this is what I would like to say about the statistical rigor. So my workshop will have two parts. The first is regression models, and the second part is statistical rigor. And this will be the rigor part. So we want to find discoveries, but meanwhile, we always want to make sure that we are doing correct things. We don't want to identify too many false discoveries. And finally, I'd like to introduce how to do this permutation sanity check. Actually, I would, in the previous work, in the previous example, I have shown a simple way to do the sanity check. And I just permute the condition. This is one way, and that is a simple way. And here I'd like to introduce a better way to do the sanity check. And this is to permute every gene separately. So I like to use the second dataset as an example, the nicotine binomial dataset as an example, to see how sanity check can be used. Okay, so we still look at this dataset, and what we can do is to random sample this dataset for each column. So we can use this function called apply function. this function will apply the same function to each row. So here we want to permute each column of this matrix. So the second argument equals 2 means column, and if it is 1, it means we want to use the same function for each row. So here, this means that we apply this sample function for each column of this matrix. And we make it the new simulcount matrix. And we call this simulcount permutation. And then we repeat all the analysis above, and we just then we calculate the p-values for each of the genes and get the p-values, and then we can use the BH procedure to control the false discovery. So the p-values. Adjusted p equals to p dot adjust p-values and method equals to BH. And we are calculate the sum, the number of discoveries. So we can see that on this permuted dataset, we will identify the large number of discoveries on the permuted dataset, and this may indicate that we are not having good results. So I just double check. Okay. And yeah, we can also try this on the correct model. For example, the previous one, so this case. So we can also generate a permuted count matrix. Okay, let's here. Okay. So here we are looking at the first data set, the Poisson data set, and we want to check whether the Poisson regression model is good. And we don't need the condition permutation because we are using another way. And we repeat all the procedures. And we can see that if we use BH procedure to do the correction, we have a small number of discoveries. So this is small, but the wrong model has large number of discoveries, and that's different. And that's how we can use this way to check whether a model is good or not. So I think that's all I like to say about this, and that's everything I like to cover. And so do you have any questions? So to summarize, we first introduced several regression models, starting from simple linear regression. And we introduced this format, these target functions, and how to solve this function. And then we introduced multiple linear regression and generalized linear regression, including logistical regression, Poisson regression, and binomial regression, negative binomial regression. And for each of the regressions, we can do different kinds of hypothesis testing regarding the coefficients. You can test the coefficient for one specific predictor or all predictors or some of the predictors. And finally, I use some examples to show how we use regression models to do the DE analysis. And I also show how model misspecification may do harm to the regression results and why we need to get rid of these problems. Okay, that's all I like to share today. And do you have any questions? Okay, if not, maybe we can just stop here and I will stop the recording.